When we write programs in Rust, we tend to focus more on how the memory layout of our program will be. If you don't do some upfront design of your data structures, the Rust compiler will likely make things difficult because of its ownership models and lifetimes. It's important to understand the memory layout of individual data types for better intuition when writing the programs and dealing with compiler errors. In this video, we will be discussing what happens when an operating system executes your binary, the memory layout of common data types like integer types, tuples, slices, vectors, strings, structs, enums, smart pointers, trait objects, and the various Fn traits. When you write a Rust program, you usually either invoke the Rust compiler directly or through cargo to generate an executable file. You can then execute it using a terminal or by double-clicking it on some operating systems that support it. Such an executable binary stores data inside it in specific formats. On Linux systems, the most common format is ELF64. Each operating system like Linux, Mac, and Windows uses a different executable format. Even though the binary format is different, how it gets executed remains almost the same across all these operating systems. The executable format basically says the first X bytes will be some header, the next Y bytes means something else, and so on. When you execute the binary, the kernel provides a continuous range of memory addresses for the program to use. This is not the actual memory address in RAM. The kernel and the hardware will map them to actual physical memory addresses when the program starts to use them. This is called the virtual address space of the program. A running program is called a process. From a process's point of view, it sees a continuous range of memory from 0 to the highest value. The executable format like ELF64 specifies a set of segments that the kernel will map into the memory when you execute the binary. The number of such segments varies depending on the compiler. I'm only showing the most important ones for our purpose. The compiler takes the code that we write in a high-level language like Rust and converts it into machine instructions that a CPU can execute. The text segment contains these executable instructions. The text segment is also known as the code segment. These instructions vary depending on the CPU architecture. For example, the binary compiled for x86-64 CPU won't work on an ARM64 CPU. The text segment is a read-only part. The running program cannot change it. The data segment contains initialized static variables, that is, global variables and local static variables which have a defined value and can be modified. The BSS stands for block started by symbol, and this segment contains uninitialized global variables. The kernel maps some additional data like the environment variables, the arguments passed to the program when executing it, and the count of the arguments. The stack segment is allocated after this, at the high end of the memory address. I mentioned that the running program is called a process. This is an abstraction used by the operating system to store all the details like the process name, process ID, etc. A process will have at least one thread of execution. Each such thread will have its own stack. On 64-bit Linux systems, Rust programs use an 8 MB stack for the main thread. For any thread your program might create, Rust standard library supports specifying the stack size. The default value is 2 MB. Even though 8 MB is the stack size of the main thread, the 8 MB is not immediately allocated. It's only allocated by the kernel when your program uses it. The stack grows downwards, that is towards the low memory. It can only grow up to the total stack size of that thread, that is, in the case of the main thread, up to 8 MB. If your program's thread uses more than the stack memory, it will be terminated by the kernel, and you will see a stack overflow error. The stack memory is used for executing functions. We will investigate more of that in a minute. The last segment we are interested in is heap memory. Unlike stack, this is not per thread. All threads of the same process share a common heap memory area. The heap memory grows upwards. Operating systems usually provide some ways to inspect these memory mappings of a running program. On Linux, this can be seen in the maps file specific to a process under the /proc directory. For example, the one shown here is part of the memory mapping of a running ls command. You might have wondered if the heap and stack memory areas will overwrite since both grow towards each other. If you check the difference between the highest address of the heap memory and the lowest address of the stack memory, the difference is around 47 terabytes. So, it's highly unlikely that either one of them will overwrite the other. The kernel provides guards to abort the program if such a situation arises. Note that these are virtual addresses. The kernel can use such large address ranges even if your computer only has 16 gigabytes of RAM. The virtual memory is only mapped to the physical memory when your program uses them. The memory address range is determined by the word size of the CPU. The word size of a CPU basically means the amount of data the CPU can process at a time. The word size of a 64-bit CPU is 64 bits or 8 bytes. Most, or all the registers of a CPU will also have the same size. A 64-bit CPU can address from 0 to 2 to the power 64-1, which is basically the value by setting all the 64 bits to 1. This is a huge value. This was the limitation with the older 32-bit CPUs. It can only address up to 2 to the power 32 memory addresses, which is only around 4 gigabytes. Currently, on 64-bit CPUs, we only use the 48 bits for memory addressing purposes. With 48 bits itself, we can address up to around 282 terabytes of memory. Out of this, only the first 47 bits are used for the user space memory. That means around 141 terabytes of virtual memory is allocated for the program, and the higher 141 terabytes is reserved for the kernel's use. With 47 bits, the highest address you can use is this value. So, if you check the memory mapping of your program, you are likely to see the stack at around this value. Next, let's dive into the purpose of the stack memory region. In this example, there is a main function which calls the add1 function. We are not spawning any threads, so there is only one thread of execution here. We saw that the total allowed stack size for the main thread is 8 megabytes. Let this white box represent this total 8 megabytes region. The memory is only allocated when the program uses them. The main purpose of the stack memory is to store data of the currently executing function. This includes the function's parameters, its local variables, and its return address. The total memory allocated on the stack for the execution of one function is called its stack frame. Here, the main function is the entry point. First, a stack frame for the main function is created. Main has a local variable a with a value of 22. Main also has another local variable b, which is also an i32 data type. The i32 data type requires 4 bytes. The stack frame of the main will also contain enough space to store it. The top of the currently used stack is tracked using a stack pointer. The main function calls the add1 function. So, a new stack frame is created with enough memory to store its data. The stack pointer is changed to the current top of the stack. The add1 function accepts an input parameter I, which is an i32 data type. So, 4 bytes will be reserved for it on its stack frame. The add1 function doesn't have any local variables. It also stores a return address. This is the next instruction in the main function to which execution should return when the add1 function completes. Once the add1 function returns, the return value 23 is stored in its local variable b. Also, the stack pointer is changed. Note that the stack frame of add1 isn't deallocated, it will just be overwritten when your program calls the next function. Let's focus on what it took to allocate on the stack. The allocation and deallocation only required incrementing and decrementing the stack pointer. Allocating on the stack is fast because it doesn't require you to make any system calls. There are also some limitations. Only variables that have a fixed size known at compile time can be stored on the stack. Also, you cannot return a reference to a local variable defined in another function. This is obvious from the working of the stack that we just saw. Let's say you tried to return a reference to the local variable defined in the add1 function. But when add1 returns, it's essentially like deallocating its memory. When the next function is called, its stack frame will overwrite this memory. In a language with a garbage collector, the compiler will automatically detect this, allocate that variable on the heap memory, and return a reference to it. but there is some extra cost to allocating on the heap. We will get into the details of heap memory in a minute. Since Rust doesn't have a garbage collector and forces you to make such heap allocation explicit, the compiler will not even compile this code. If you read the error message, by now it should be obvious to you why the compiler raises such an error. Next, let's see the purpose of the heap memory. Here, our main function is calling the heap function. Just like we saw, it creates a stack frame for this function. Then we allocate the value 23 on the heap memory, using the box and storing it in the local variable b. So, the stack frame of the heap function will have enough size to store this box. Since the box is nothing but a pointer, the value stored in b is the address of value 23 in the heap. On 64-bit systems, the memory allocated for pointers is 8 bytes, so the size of b on the stack is 8 bytes. The value pointed by it is 23, which is an i32 type. So that needs 4 bytes on the heap. The heap function returns a box of i32. The return value is stored in the local variable result of the main function. Whenever you assign one value to another, its stack allocation is copied. In this case, the 8 bytes used to store the address are copied from the heap function's stack frame to the result variable. Now, even though the stack frame of the heap function is deallocated, the result variable contains the address of the data in the heap. The heap allows you to share data. We also mentioned that each thread has its own stack, but they all share the common heap memory region. Let's suppose your program allocated more and more data on the heap, and the currently allocated memory is almost full. Programs usually will have a memory manager which will request the operating system for more heap memory using system calls. In the case of a Linux operating system, this is done using brk or sbrk system calls. This increases your program's heap size, and thus the total memory used by your program. In Rust, the heap allocators are described by the global alloc trait. The global alloc trait defines the functions that a heap allocator must provide. As a programmer, you rarely use it directly. Instead, the compiler will automatically insert the appropriate calls to the trait methods when needed. You might be familiar with the malloc function and the C standard library. This is not a system call. The malloc will call the brk or sbrk system calls when more memory needs to be requested from the kernel. Rust's memory allocator uses this malloc function provided by the C library. When you use a tool like LDD to inspect the dynamic dependencies of your binary, you will see one of them is libc. This means that this Rust binary expects the C standard library or libc as a shared object or compiled library at that location. This is a safe assumption because libc is more like part of the operating system, and such dynamic linking allows Rust to have smaller binary sizes. Also, the memory allocator doesn't always use system calls to allocate more memory on the heap every time your program allocates something on the heap using box or something similar. The program's memory allocator requests memory in chunks to reduce the number of system calls. Also, unlike stack, memory is not always freed from one end of the heap. And when some regions of memory are freed, it's not immediately returned to the operating system. The memory allocator keeps track of the memory pages that are used and which are free so that when more data needs to be allocated on the heap, it can do it without waiting for the operating system or kernel. I assume you've got some idea why the heap allocation comes with a bit of performance overhead compared to the stack. It may involve system calls and the memory allocator will have to find a free slot on the heap for every allocation. Now let's start looking at how Rust's data types are laid out in memory. Both signed and unsigned integer data type shows the number of bits each one can hold. For example, both i16 and u16 take 2 bytes in memory. They are allocated completely on the function stack frame. The i-size and u-size data types are machine word size dependent. On 32-bit systems, they use 32 bits or 4 bytes, and on 64-bit systems, they use 8 bytes. The char data type stores Unicode characters. Some example values are shown here. They take 4 bytes in memory. They are also allocated on the stack. A tuple is a collection of values of different data types. Here variable a is a tuple consisting of a char, a u8, and an i32 data type. Its memory layout is just placing its members next to each other. In this case, the char takes 4 bytes, U8 takes 1 byte, and a 32 takes 4 bytes. Since all these members are stack-only data types, the tuple is also allocated completely on the stack. Note that even though it looks like this tuple will only use 9 bytes in memory, that's not the case. You can use the size of function in the standard library to inspect the actual size of a data type. Every data type also has an alignment value, and the total bytes allocated for the data type should be a multiple of this alignment value. This is not particular to Rust. Every compiler does this. This is done so that CPUs can read data more efficiently. The align of function shows the alignment value of a data type. For this tuple, the alignment value is 4. Rust will use 12 bytes to represent this tuple even though it only needs 9 bytes. An extra 3 bytes will be added as padding. Next is the reference data type. In our code, the variable a is an i32 data type, and we store 25 in it. Variable b is a reference to a. From now on, I won't be showing the actual number of bytes a data type takes. We will be focusing more on the overall structure, and whether they are stored on stack or heap. Here, a is stored on the stack, and it takes 4 bytes. The reference b is also stored on the stack, and it will contain the address of the variable a. Storing addresses requires a machine word, so on 64-bit systems, variable b takes 8 bytes. If we store a reference to b in another variable c, the data type of c will be a reference to i32. The variable c will also take 8 bytes and will contain the address of b. Note that the reference can also be pointers to data on the heap. The mutable references also have the same layout in memory. The difference between shared and mutable references is in how they can be used, and the additional restrictions the compiler enforces on mutable references. Next is the array data type. An array is fixed in size, and that size is part of its data type. Here, each i32 element of the array will be placed next to each other on the stack. However, it's not possible to change the size of the array after it's created. Remember, only data types whose size is fixed and known at compile time can be placed on the stack. The resizable or growable alternative to an array is a vector data type. Here, the vector v also contains the same elements as that of our array. However, the data is allocated on the heap, and the function stack frame where v is declared will contain 3 machine words. The first word contains the address of the heap allocated data. The rest of them are used to store the capacity and the length of the vector. The capacity field indicates how much memory is reserved for the heap data. When we add more data to the vector, if we haven't reached its currently allocated capacity, Rust doesn't have to allocate more space for the heap data. When the length and capacity become the same and more elements need to be added to the vector, Rust will have to allocate a larger size array in the heap, copy the elements from the current location to the new array, and update the pointer to the new memory location. Notice that the stack side of the vector always remains fixed size. Another related data type is a slice of t. Notice how similar the data type is to a fixed size array, except we don't need to specify the size and the data type. A slice is like a view of some elements of an underlying array. Here, S1 represents the first 2 elements of our array, and S2 represents the first 2 elements of the vector in the heap. The problem with a slice is that it doesn't specify the number of elements, which means, at compile time, Rust doesn't know how many bytes are needed to represent a slice. This also means that you cannot store it in variables since it doesn't have a known size, and thus cannot be allocated on the stack frame of a function. Such types are called dynamically sized types. There are other dynamically sized types like string slices and trait objects. We will discuss them in a few minutes. Almost always, we use a reference to a slice. We already saw that a reference is just a pointer, and takes 1 machine word to store the address to which it is pointing. When you use a reference to a dynamically sized type, like a slice, Rust uses an additional machine word to store the length of the data. This kind of reference is also known as a fat pointer since we are storing additional information along with an actual pointer. Since the reference to slice can be represented using 2 machine words, it can be stored on a function stack frame. Remember that the actual data pointed by the reference can either be on the stack or the heap. Next, we will discuss the string data type. The string data type has the same memory layout as that of a vector. The only difference is that strings are guaranteed to be UTF-8 encoded. If you store a string literal directly in a variable, the data type of that variable will be a reference to the string slice. This string data is not allocated on the heap memory. Instead, it is stored directly in the compiled binary. As far as I know, Rust doesn't specify in which segment the string will be stored, but it's likely to be in the code segment itself. These kinds of strings also have a static lifetime, meaning they are never deallocated and are available throughout the life of your program. Just like a reference to a slice, a reference to a string slice is also a fat pointer. It is represented using two machine words, one for storing the starting memory address of its data and another for storing the length. It's possible to get a portion of a string using range operations, but this returns a string slice. However, since a string slice doesn't have a known size at compile time, it cannot be stored in the stack frame of a function, and thus Rust doesn't allow you to assign it to a variable. So, you should use a reference here too. Next is the struct data type. Rust has three kinds of struct types. The struct shown here is the one with named fields. There is also a tuple-like struct and a unit-like struct. The unit-like struct doesn't have any data, so the Rust compiler will not even allocate any memory for it. The other two have a similar representation based on their members, and it is very similar to the tuple data type that we saw previously. Let's look at how a value of the first struct with named fields will look in memory. It has two fields, a vector and a tuple. The stack representation of the struct will be equivalent to placing the member elements side by side. Here, the vector member will take 3 machine words, and the tuple will take another 2. Remember that we are ignoring the alignment and padding here also. If the enums member has elements, those values will be allocated on the heap. The next data type is enum. Just like structs, Rust supports a few different syntaxes for enums also. The one shown here is a C-style enum. In memory, they are stored as integers starting from 0. Rust compiler will choose the shortest integer type that can store the highest variant of that enum type. Here, the highest value is 1, and it can be stored using 1 byte. You can also specify integer values for variants. Here, the largest value is 404. 2 bytes are required to store it in memory, so each value of this enum will require 2 bytes. In the next example, our enum has 3 variants. The empty variant doesn't store any other values. The number variant has an i32. The array variant has a vector of i32. First, let's look at the memory layout of the array variant. There will be an integer tag, here it is 2. Then there will be 3 machine words for storing the vector. The compiler will also add some padding to make the proper alignment. In total, this variant takes 32 bytes on my 64-bit computer. Now let's take a look at the number variant. It stores a single i32, which takes 4 bytes. It also has an integer tag value of 1, which will only take 1 byte. Since all variants should have the same size, the compiler will add padding bytes to make it 32 bytes. In the case of the empty variant, it only requires 1 byte for storing the integer tag. However, a padding of 31 bytes must be added for every use of this value. The memory required for values of an enum is determined by its largest variant. The obvious trick to reduce memory usage is to limit the size of the largest variant. In this example, instead of storing the vector directly inside the array variant, if we choose to store a pointer to a vector, the memory required for this variant is reduced in half. A box is a pointer to some memory allocated on the heap. So the stack part of a box only requires 1 machine word to store the memory address of the heap allocation, which is 8 bytes on a 64-bit system. The memory layout of a boxed vector will be like this. On the function stack frame, 1 machine word will be allocated to store the memory address to which it points. In the heap, the 3 machine words will be stored which is required to represent a vector. Remember that if the vector has values, those values also will be in the heap itself, and a pointer to that allocation will be stored in the pointer field of the vector. One of the most used enum is the option. It is used to represent values that can be null or empty. For example, suppose you want to represent a pointer to an i32 value allocated on the heap. You also want to represent its zero value, that is, the case when you haven't even allocated the value. In other programming languages with pointers, it is usually represented using a null or null pointer. In Rust, it is represented as an option of box of i32. This allows the Rust compiler to ensure that your code doesn't make any mistakes with the pointer like dereferencing a null pointer. The option has two variants. The none variant doesn't store any values, it only stores the integer tag. The sum variant stores actual data along with its integer tag. In this example, since the t is a box pointer, one machine word is required to store it. If you think about it, there is some memory wastage here. Other programming languages can represent a pointer with one machine word, but Rust requires another byte for integer tag, and then some padding because of this extra byte. The Rust compiler can make some optimization if the value stored in an option is a box or other similar smart pointer types. Since none of the smart pointers are allowed to be 0, Rust can represent an option of box of i32 using a single machine word. It doesn't need the integer tag. A value of 0 can be used to represent the none variant, and if the value is not 0, then it's the sum variant. This makes Rust's wrapping of smart pointers inside the option equivalent to the pointers in other programming languages. The difference is that Rust can eliminate null pointer dereferences. Before going any further, let's quickly see the difference between copying and moving in Rust. For primitive data types like integers, if you assign a variable to another, the new variable gets a copy of the data stored in the right-hand side variable. Rust does a bit-by-bit copy of the value here. This is possible because these values can be represented only using bytes on the stack. Rust allows you to use both variables in later parts of your code. The stack frames are automatically cleaned up when a function returns. Now, let's look at values that require some data on the heap. Here, we have a vector of heap allocated strings. Each string is represented using 3 machine words for storing a pointer to the actual data, its capacity, and length. Within the memory allocated for the vector in the heap, these machine words used for storing the string header will be placed side by side. The actual bytes used to store the value of the strings will be allocated somewhere else in the heap, and pointers to that memory will be saved in the string headers. Within the stack frame of the function, 3 machine words will be allocated for variable v to store the header of a vector, and it will have a pointer to the heap allocation. In terms of ownership, we say the variable v owns the whole heap allocation. Since Rust doesn't have a garbage collector, this variable is responsible for cleaning up the heap allocation when it goes out of the scope. Next, we assign variable v to a new variable v2. Assume we did a bit-by-bit copy of the stack side of the variable. At this point, v2 will also have a pointer to the same heap value. This is what happens in a language with a garbage collector. This is cheap in terms of memory since we only have to copy a few bytes no matter what the size of the memory in the heap. The garbage collector can keep track of the number of references to the heap allocation, and when all of them go out of scope, the garbage collector will deallocate this memory. But Rust doesn't have a garbage collector, instead, it has ownership models. At this point, it's not clear who is responsible for cleaning up the heap memory. Another option is to create a copy of the entire heap value when assigning it to a new variable. However, this can cause increased memory usage and lower performance due to all those copies. Rust's policy is to make such choices explicit. If you want to create a variable with its own copy of the entire data allocated on the heap for that value, you should explicitly use the clone method. If you don't ask it to clone this value, the Rust compiler doesn't allow you to use the variable v in the later part of your code. The value is said to be moved. Now variable v2 is the owner of the value, and it will be deallocated when v2 goes out of scope. Sometimes you want multiple owners of the same value. In many cases, you can use normal references to share value, but the problem with that approach is that, when the owner goes out of scope, you can't use those references anymore. Instead, what we want is a situation with shared ownership, where every variable is an owner of the value, and the value will only be deallocated when all of them go out of scope. This is the purpose of the RC Smart Pointer. When you wrap a vector inside an RC, the three machine words that constitute the vector header are allocated on the heap along with some additional memory to store the number of references to the value. On the function stack frame, the variable v will consist of a single machine word, which will contain the address of heap allocation for RC. You can then create a second variable by cloning the first RC variable v. This clone doesn't clone anything in the heap memory. Instead, it creates a copy of the stack side of the pointer and simply increments the reference count value. Now both v and v2 are owners of the same data. This is why it is called a reference counted pointer. But RC has a limitation that the value pointed to it is immutable. There are ways to get around this using interior mutability, but we won't be discussing it in this video. When each of the shared owners goes out of scope, the reference count is decrement, and when it becomes 0, the entire heap value will be deallocated. Rust has some special marker traits like send and sync. Basically, if a type is send, it means a value of that type can be moved from one thread to another. If a value is sync, it means multiple threads can share the value of that type using shared references. The RC smart pointer is neither send nor sync. Assume that two threads had RC pointers to the same data. At some point, if your code in both threads clones the RC pointer, both will try to update the common reference count value. This is a data race. One of the main advantages of Rust is that it eliminates all such memory-related bugs. If you really want shared data across threads like this, use the atomically reference-counted pointer arc. The working of arc is almost the same as RC, except that the reference count is updated by atomic operations, which is safe to do from multiple threads. However, there is a small extra performance cost for atomic operations. That's why you have RC and arc as separate types. If you don't need it, you don't have to pay the extra cost. Note that by default, arc is immutable, so even though multiple threads have a pointer to the same data, they are not allowed to mutate the data. If you need mutable access to shared data from multiple threads, you can wrap a mutex inside an arc pointer. Now, even if two threads try to access the data at the same time, they need to acquire the lock first. Only one thread can have the lock at any time, and thus there can only be one writer at a time. The mutex guards the data. Next is the trade object. A reference to a trade type is called a trade object. There are multiple ways to convert a concrete type to a trade object. In the first example, the conversion happens when assigned to variable w, and in the second example, the conversion happens when you pass the concrete type to a function that accepts a trade object. In both cases, a vector of U8 is converted into a trade object that implements write. In memory, a trade object is a fat pointer consisting of two pointers. Each trade object, therefore, takes up two machine words. The first one is a pointer to the value. In this case, the value is the vector. The second part is a pointer to the table representing that value's type. This table is called a virtual table, or vtable. The vtable is generated once at compile time, and shared by all objects of the same type. The vtable contains pointers to the machine code of the functions that must be present for a type to be a writer. Rust automatically uses the vtable when you call a method of a trade object. Notice that the write is also a dynamically sized type, like slices. That's why we always use a reference to it. Also, in these examples, we converted a vector of U8 to a writer trade object. This is possible because the standard library implements the writer trait for a vector of U8 type. We just saw that Rust can convert ordinary references to trade objects. Rust can do the same for smart pointers like box and RC. In those cases, they will also become fat pointers. A box of write means a value that owns a writer in the heap. In all cases, whether it is an ordinary reference or a smart pointer, at the point where this conversion happens, Rust knows the reference's true type. In this case, a vector of U8. So it just adds the address of the appropriate vtable, turning the regular pointer to a fat pointer. Next is the function pointer. A function pointer just takes one machine word to store the address of the actual machine code for the function. Here, test_func is a function that returns a boolean. We are storing it in a variable in the main function. Finally, let's look at closures. Rust doesn't have a concrete type for closures. Instead, the language specifies 3 traits: Fn, FnMut, and FnOnce. First, we will take a look at a FnOnce closure. Here, we declared the create_closure function returns something that implements the FnOnce trait. Within the body of the function, we are creating a string. As we already saw, a string is 3 machine words on the stack. Then we create a closure. A closure can use data that belongs to an enclosing function. Within the body of that closure, we simply deallocate or drop the string value we created. Remember that FnOnce is a trait, which means it only defines the behavior or what methods an object has. Rust internally uses structs to represent closures. Rust will create an appropriate struct depending on the variables the closure uses and implement the most appropriate traits on that struct. The actual signature of the closure traits is a bit complex. What I'm showing here is the simplest version of it. In this case, our closure will be represented using a struct like this. It only has one member, the string it captures from its enclosing function. The call once is the function that must be implemented on the object for FnOnce. Since the struct used to represent the closure only has the string field, its memory layout will be the same as a string. Notice the syntax of the call once method. It consumes the self. This means it can only be called once. This is obvious in this case. If we had called the closure a second time, it would try to drop the string that was already deallocated. In the next example, we create a FnMut closure. This is FnMut because we are mutating the variable I that was defined in the enclosing function. In this case, the struct used to represent the closure will have a mutable reference to the original variable I. Also, the callMut method required by the FnMut trait takes a mutable reference to self, which means we can call the closure any number of times. Notice that in the first code snippet, I'm declaring the variable f, in which closure is stored as mutable. This must be mutable because the callMut method takes a mutable reference to self when called. Try making f not mutable. The compiler will show an error message which makes sense when we understand the details we just saw. The error essentially says calling the closure requires borrowing it as mutable. The last among the closure traits is the Fn trait. In this example, within the body of the closure, we simply print the value of the message variable. The print macro takes arguments by reference. So, Rust will implement the Fn trait here. The struct will only have a reference to the actual string. Also, notice that the call method required by the Fn trait takes a reference to self. So you can call the closure any number of times, and the variable in which closure is stored doesn't have to be mutable. In the next example, we are using the same closure that we just saw, but instead of storing it in a variable in the same function, we are returning it. But in this case, the compiler will show an error message like this. It says that the borrowed string message may outlive the current function. If you think about the memory layout of the struct created for representing the closure has only a reference to the string. We already saw at the beginning of this video that when a function returns, its stack frame is deallocated. So, our closure cannot have a reference to a memory location in that function's stack frame. Rust is asking us to use the move keyword to explicitly say that we want our closure to take ownership of the thing we use inside the closure. When we use the move keyword, the struct representing our closure no longer has a reference, but the actual string itself. Till now, we have only seen closures that have only one member. This example shows a closure that takes 2 objects, a string, and a vector. There isn't anything special here. The memory layout of the struct used to represent this closure will be equivalent to placing the stack side representation of both string and vector, side by side. This pattern follows in other places also. For example, the async ecosystem heavily uses the future trait. In memory, the compiler uses an enum to represent the actual object and implements the future trait on it. I'm not going into the details of it. I will provide a link in the description, which explains the implementation details of async functions.